Right, so we continue from where we stopped in flow networks and for the Fulkerson algorithm. If you have not subscribed, please click on the subscribe button to subscribe to my channel so that you get notified when I make new lessons. And also, in this way, you encourage me to continue making these videos for you. So we are going to be discussing cots in flow networks. So one thing I want to tell you is understanding cots is very important because that will help you also understand other things like the max flow. So let's see. What really is a cot? Suppose we divide the nodes of the graph into two sets A and B so that S, the starting node or the source node belongs to A and T, the sink, belongs to B. Then any flow that goes from S to T must cross A into B at some point and therefore use up some edge capacity from A to B. What is all of this? What it simply means is that if you have a flow network, let me take my pen again so that I can illustrate. If you have a flow network, let me use from here. And this is S, and this is T, and this is A and B. So you have this flow network. You can actually cut it. Let's say, let me use another paint, so that another color, so that this becomes clear. So if I cut it this way, we have that S now is what? Is A, S and A, and T is equal to B and T, or we can say A is equal to S and A, and B is equal to B and T. So we actually divide the nodes into two parts, but the key thing is that the source node should be in the first part, in the first segment, and the second one should be which is the T, which is the sink, should be in the second partition. If we cut this like this, we have not achieved anything because in this case we have the source and the sink in the same place. So let's see how we can use the concept of cuts to actually solve the max flow problem. Remember, the max flow problem says find the maximum flow across the network. Okay, so we have this suggests that each of such cuts of the graph puts a bound on the maximum flow possible on the maximum possible flow value, right? So what it means, if you cut it correctly, it means that all the flows going across the first partition must enter the second partition. I think an example will make it clear. Therefore, we need to develop an algorithm that shows that the maximum flow, max flow, equals the minimum capacity of a cut, mean cut. This will become clearer in the next screen. But what I want you to take note of that is the cut puts a bound on the maximum possible flow value. How does it play out? We can see that finding the cut of minimum capacity in a flow network turns out to be the same as finding the maximum flow. Now comes an example. So the first thing we are going to do is to find the maximum flow here, and then we find the minimum cut, and then we see that the both of them are equal. So let's go. The first thing, find maximum flow. Let's take certain series of steps. So I use a red pen. Determine the max flow. Step 1, push 3 through AB, BE, and EZ. So this place we have 5. Here we have 6 capacity. We have what? Here we have 6. So we can put a flow of what? Of 3 here. Put a flow of 3 here, and a flow of 3 here, right? So here we have a flow of 3, because we say that the flow of the network is the flow that comes out from the source or goes into the sink. So here we have a flow of 3, but the capacity of this network is what? Is 12. Yeah, 6 plus 6 is equal to 12. So we are not using up the capacity of this network. Alright, so let's try another thing. So let's try to push 3 through AC. Meanwhile, after the first step, we have a flow of what? Of 3. It's not maximum because the maximum is the capacity of this network is what? Is 12. So let's push 3 through AC, CE, and EZ. AC, which is here, 3. CE, which is here, and EZ. So if we put 3 here, it means that this becomes what? It becomes 6. So at this point, we have a flow of 3 plus 3, 6, which is also 6 here going into Z. The numbers in black are the capacity. So at this point, we have 6. But it seems we are still far-fetched because we say the capacity is 12. So 6 is really too small. Let's try to do a little more. Let's try to push 1 through AC, CD, and DZ. AC, CD, and DZ. So remember, we are doing it part by part. So in the first one, we take a particular part from the source to the destination, and like that. So let's try to see what we can do on this. Let me take my pen. So we are saying we need to put what? 1 through this place. So if we push 1 through this place, so we have here, we have 4. We have 1, which is CD, and DZ. So here we have 1. So at this point, the value of our flow is what? 3 plus 4, 7, 6 plus 1, 7. So 7. I think we are still far from 12. So let's try to take one more step. Let's try to, because we see that this BD is not used. So let's try to see if we can push 2 through this place. So if we push 2 through AB, from AB, BD, and DZ, 2. And let's see how it goes. So at this point, this one becomes what? It becomes 5. And this one becomes, this one we push 2 because BD, and here we push 2, becomes 3. So at this point, we have 5 plus 4, 9. We have 6 plus 3, 9. So let's say 9. I know that 9 is actually the maximum flow. So how do we do it? We need to verify using mean cut. So let's start by finding the mean cut. To determine the mean cut, place a cut line through all the edges from A that is saturated, right? So let's do it together. So from A, we find the parts that are saturated. So let's try A to B. Is it saturated? Yes, because we have 5. So we can't place any more flow here. So it's saturated. We place a cut line. A to C, is it saturated? No, it's not saturated. So we can't place a cut line there. C to E. This C to E. From here to here, is it saturated? Yes, it's saturated. We place a cut line. C to D, is it saturated? Yes, it's saturated because 1 we place a cut line. So I think you get the point. So now we can complete the cuts, and now we have created a cut. If you create a cut this way, that cut is the mean cut. So calculate the capacity of this cut. Add all capacities of edges pointing from A to Z. So let me take a pen. Sorry, so this is A, and this is The second network is B. So this edge is pointing from A to Z, this edge is pointing from A to Z, and this edge is pointing from A to Z. So let's calculate capacity of the cot A and B, A to B, is equal to what? 5 plus 4, 5 plus what? Plus 3 plus 1, which gives us what? 9. And what do we have here? Equal to 9. So max flow of 9, and this is mean cot. So as you can see, it worked perfectly. So maybe you can pause this video and try to take your head around it and see that you understand exactly what is happening here. So we have done it manually, and we are getting close to Fulkerson algorithm because we are trying to do this using an algorithm, but now we proved it manually that it works. Alright, so we are going to start with Fulkerson algorithm, and that we are going to do in the next tutorial. I'd like to thank you for viewing. We'll see you in the next tutorial, and also remember to subscribe to my channel.